Um, Good morning. So I'm going to tell you a few things about radiative processes in cosmic objects. So this is a radio astronomy winter school. You are uh, learning about astronomy, and particularly astronomy that can be carried out at radio wavelengths. And radio is one type of radiation that we receive from cosmic objects. And you would have already seen that when you look at the sky in radio, it looks quite different from if you look up at the sky and see it uh, with your naked eye, right? So these are the various kinds of radiation that we receive, and our knowledge of the universe derives from the radiation we receive, because we, by and large, cannot go to most cosmic objects and touch or feel or see them for ourselves from close by. So understanding the processes of radiation and the information it carries is vital to the practice of astronomy. So a naked eye view of the sky is dominated by stars. So if you go out at night and look up at the sky, you will see a view somewhat like this. If you happen to be in a dark location and Milky Way above your head, so it's a spectacular view, mostly dominated by stars. But the human eye, through which we see the sky, uh, is limited to a tiny fraction of the electromagnetic spectrum. So if you look at the electromagnetic spectrum, uh, here on the right, uh, you can see that it is only this tiny bit which is the visible light, which our eyes are sensitive to. Excuse me. But the electromagnetic spectrum extends in both directions far, far longer, starting from gamma rays at the shortest wavelengths to radio at the longest wavelengths. And what you have come to learn is that cosmic sources radiate over this entire electromagnetic band. And if we restrict ourselves to visible light, we are mostly blind to many, many different types of phenomena that go on in the universe. So multi-wavelength study of objects has now become a standard practice in astronomy. What I've shown here on the left is a picture of a galaxy taken at multiple wavelengths. So the top picture here is a composite of pictures taken at different wavelengths. The optical view is the one over here. So it's a galaxy called Centaurus A. When you look at it in X-rays, the view is quite different. You see a strong jet emanating from the center. If you look at radio, then you do see the presence of the jet and the effect that the jet is having at even larger distances. And a specific radio wavelength near the hyperfine transition of hydrogen at 1420 megahertz or 21 centimeter wavelength gives you yet another view, which maps the location of the distribution of neutral hydrogen gas. So if you look at the sky, or if you look at any object at different wavelengths, you see different views. And that is because of the different ways these radiations come about. And so the learning about them, how these radiations come about, and what information they are telling us about the object is the main aspect that I would like to cover in this in these lectures on radiative processes. So we said that when you look at the sky with the naked eye, mostly what you see are stars. And the stars have a very characteristic spectrum. They peak somewhere in the visible band. Depending on the mass of the star and the brightness, the peak of the emission could be at different wavelengths within the visible band, more or less. So from the hottest, which is on the top here, to the coolest stars we know, we can see that the peak of the emission moves to longer and longer wavelength. The horizontal axis here is wavelength. So the peak brightness moves from blue to red as you go to cooler and cooler stars. This distribution of light as a function of wavelength is what is called a spectrum. And this spectrum in general carries a lot of information about the object that we are studying. In case of stars, the spectrum is by and large a thermal blackbody continuum, on top of which there are some narrow spectral lines you would see here. These are absorption lines caused by the atmosphere lying above the star. So they absorb the light coming from the star and produce these lines. But the underlying continuum is a thermal blackbody continuum. So let's look at that a little bit. Right. So what I show here on the left is the spectrum of the sun. If you measure it with an instrument as a function of wavelength, you can use a disperser and use different filters, whatever, use a grating, and you'll get a spectrum like this, which is shown in red in this left-hand diagram. It is approximated very well by a 5780 Kelvin blackbody, which is shown in the yellow line over here. However, there are some departures, on top of which there is some excess emission in the ultraviolet. There are some spectral lines in the visible band and so on. And these are primarily caused by the atmosphere of the sun and the corona lying above the sun. The underlying continuum spectrum is by and large fully described by this 5780 Kelvin blackbody. Now, what is a blackbody spectrum? The blackbody spectrum is uniquely defined by the Planck function, which is written here. Planck function B as a function of frequency nu is given by 2h nu cubed by c squared times 1 over e to the power of h nu by kt minus 1. So this is a unique function. It's a function only of temperature. So here I plot the blackbody function in log-log scale, log frequency on the horizontal axis, log intensity on the vertical axis. And what you can see here, the shape of the function is self-similar, and the size is uniquely determined by the temperature. So as you go from one temperature to another, the function changes. Its peak frequency moves to higher and higher frequencies as you increase the temperature. And the shape of the function remains the same. It just scales up to different sizes. And it's also important to note that the blackbody function at a higher temperature completely envelopes the blackbody function at a lower temperature. That means it is higher at any frequency whichever frequency you choose, the Blackbody function at a higher temperature is higher than that of a Blackbody function at a lower temperature. So that's a standard characteristic of the Planck function. So what we can see from this Planck function is that the function has a well-defined peak and the intensity falls off on either side. And this peak corresponds very close to the place where the argument of this exponential is close to 1. So that is h nu of the order of kt. It's h nu close to kt. That's where the peak occurs. So if you take frequencies which are much smaller than kt over h, then the intensity is less. If you take frequencies which are much larger than kt over h, then again the intensity is less. So let's remember this property of the Blackbody function, that its peak is determined by the temperature, and the intensity goes down on either side. One thing I wanted to mention but forgot to say is that all thermal sources would produce a Blackbody-like function as their intensity distribution if they happen to be optically thick. Now, what does one mean by optically thick? We'll come to as we go along in this lecture. So any optically thick thermal source is going to produce a Blackbody emission. And the stars happen to be optically thick thermal sources. And so they all produce this Blackbody emission. Okay. So now let us go back to the very basics of the origin of electromagnetic radiation itself. So electromagnetic radiation is created by charged particles. What you see from the sun is the combination of emission produced by many charged particles which reside inside the sun. But if we look at the process at the level of an individual single charged particle, then we can go to electrodynamics and then ask, what is the electric field that an arbitrarily moving charged particle can produce? And the answer is this, which is shown here. So it's got two components of it. One is a field that drops as 1 over r squared. This is something most of you would have already come across often. And this is the Coulomb field. So if a charged particle is stationary and you have an observer at a distance r from the charged particle, then you have a field which goes down as q over r squared. And that's the this component of the field. There are other factors here which appear because of the motion of the charged particle. So there is a retardation factor. For example, the information takes finite time to go from the charge to the observer. So what you see now is a product of where the charge was when the information left the charged particle. So that factor is taken care of in this kappa. And then the velocity of the charged particle makes the direction to the charged particle change, and this n minus beta and it takes care of that. And there is the special relativistic Doppler factor, which is given by this 1 minus beta square. So beta is the speed of the charged particle divided by c, and beta dot is actually the acceleration of the charged particle in units of speed of light. So we have this charged particle moving arbitrarily along this blue path. At an instant, the charged particle is located here, and its velocity u is in this direction. N is the direction, is the line of sight, direction of the line of sight, and u dot, its acceleration at this point of time happens to be in this direction. So for a charge which is moving, in addition to this Coulomb near field electric field, there's also another component which appears. And this component appears when there is an acceleration, because this is multiplied by beta dot. So if acceleration is 0, this term goes to 0. The interesting thing is that this term has a 1 over r dependence, unlike Coulomb field, which has 1 over r squared dependence. So that means if you go further away from the charge, this term would become dominant with compared to this term. This is going to keep dropping as 1 by r squared. This is going to keep dropping as 1 by r. And if you take this, if you measure the electric field at a very large distance, it is this term, which is boxed here, is going to dominate. And in fact, this is the radiation field that we experience. For a moving charge, in addition to the electric field, there is also a magnetic field that is produced, and that is given by the any line of sight vector we take cross the electric field. So it will also have these two components, and magnetic field will also have a far field component, which is radiation. So the at a large distance, we do not experience the first term very much, but we experience the electric field and the magnetic field, which are both dropping as 1 over r. If you now construct the quantity which defines the outgoing flux of energy, that is a cross product of E and H. And so E cross H is the propagating energy flux per unit area at a distance r. You can see that if you take E cross H and if you take this radiation term, the term will have the product will have a dependence of 1 by r squared. But if you look at a distance r, then the total surface area at the distance r enclosing the charge is also proportional to r squared. So that's what this shows. E cross H r squared, d omega is the solid angle. So the total emitted radiation, which is E cross H r squared d omega at any given r, is now independent of r, because E cross H is proportional to 1 by r squared, and the surface area is proportional to r squared, so that cancels. So therefore, whatever distance you take, if you create a sphere enclosing the charge, it is the same amount of energy flux that is crossing that total sphere. So the net energy loss is independent of distance, and that is why this flux survives even at infinity. The total energy loss survives even at a very large distance at infinity, and therefore this represents and outgoing energy loss from the charge. And this emitted power can be, the integral can be performed, and it can be shown that this is proportional to the square of the charge, square of the acceleration, and divided by these constants. It is proportional to square of the acceleration and the square of the charge. So what you have learned then is that if a charged particle is subjected to an acceleration, then it will produce electromagnetic radiation. And it is this electromagnetic radiation that we will be able to see at a large distance. Now, in this formula, this quantity A is the acceleration defined in the frame where the charge is at rest at that instant. So this is called proper acceleration. So this is evaluated in the instantaneous rest frame of the charged particle. So in this example, if we go to a frame which is at this point of time moving at a speed u in this direction, then the charged particle will be at rest in that frame. And then in that frame, the acceleration that we will measure, that is u dot, that we will measure when u is equal to 0, is the value of A. So you should remember that if we want to use Larmor formula, this quantity A has to be always evaluated at the instantaneous rest frame of the charge. So let's go forward. Now, if the charge is moving with respect to the observer, or observer is moving with respect to the charge, then one thing happens, that is, if you take the total energy loss, as I showed you in the previous slide, d dt, that remains invariant no matter which observer you look at, as long as they're inertial observers. So the quantity which is the total power emitted is a Lorentz invariant. So two observers who are moving at two different speeds with respect to the charge will not disagree on the total energy being lost by the charge. Someone who is moving with the charge and someone who is, let's say, stationary in the lab, they will both agree how much energy is being lost by the charge per second. It's a Lorentz invariant. Now, I said that the acceleration has to be expressed in the instantaneous rest frame of the charge. So that is A0, let us call it. But a moving observer, if the observer measures acceleration with components A parallel along the relative motion and A perpendicular across the relative motion, then the measured quantities A parallel and A perpendicular are related to the proper acceleration in this manner. So it's got A parallel squared, A perpendicular squared, giving you A0 squared, but there are multiplications by these gamma squared factors. So gamma is a quantity called the Lorentz factor, defined as 1 by square root of 1 minus v squared by c squared, where v is the velocity of the charge. So the closer the speed approaches the speed of light, the larger is the Lorentz factor. As v tends to c, gamma will tend to infinity. When v is 0, gamma is 1. So if the observer is stationary, then of course A0 squared is simply A perpendicular square plus A parallel square, which is A squared. On the other hand, if there is a motion, then we have to use these Lorentz factors to transform the measured acceleration to the rest frame acceleration. So for an observer, from a moving charge, the Larmor formula can be rewritten as q squared gamma to the 4 6 pi epsilon c cube a perpendicular squared plus gamma squared a parallel squared, where I have just taken a squared, which was there in the previous slide, and replaced it with this expression. So what this does tell us is that for a given measured acceleration, the amount of emitted power that we will see has a strong dependence on the Lorentz factor. So this we should keep in mind when we talk about how much radiation we receive from a charge. The next thing that happens when we are in a moving frame with respect to the charge, or the charge is moving with respect to us, is that the pattern of radiation changes. Now, here I have shown the pattern of radiation of a charge which is moving up and down along this arrow. So it's like an oscillating charge along a line. It's called a dipole. And this dipole has this kind of radiation pattern. And this is when the average motion of the charge is stationary with respect to the observer. So the charge moves up and down, the acceleration is upwards or downwards, but the charge itself is stationary with respect to the observer. Then the radiation pattern will be like this. But if this dipole moves with respect to the observer, let's say in the horizontal direction, then what we will see is that the radiation pattern, the distribution of radiation in the direction of motion will enhance, and against the direction of motion will reduce. So what we are seeing is that although a moving observer will see the same total amount of energy loss integrated over all angles, the distribution of the radiation as a function of angle changes. So this is because of aberration, and this is called relativistic beaming. So the faster the charge moves, the narrower this beaming cone will become. So as the Lorentz factor increases higher and higher, this cone becomes sharper and sharper with a width which is proportional to 1 over the Lorentz factor. So if the Lorentz factor is 1000, then this opening angle will only be 1,000th of a radian. So you can see that it's a very narrow pencil beam in the direction of motion of the charge. However, if we integrate over all angles, the net emission, energy loss from the charge remains the same. So therefore, since the emission is now beamed within a very narrow angle, in that direction per unit solid angle, the amount of intensity is highly enhanced because energy is taken from all other angles and pumped into those small range of beaming angles. So you get a relativistic beaming which enhances power in the direction of motion of the charge. Before I go forward, I should also mention that when we talk about electromagnetic radiation and we talk about spectrum, we are always referring to something called a frequency, which I already did when I showed you the Blackbody spectrum and so on. This is the frequency of oscillation of electromagnetic field. So one can take the electric field and magnetic field that we receive. We can think of this electric and magnetic field to be composed of a large number of sinusoidal oscillations. And each of these oscillations have a frequency. And these frequencies are the ones that we mention as the frequency of the radiation. And when you have a relativistic beaming, due to Doppler effect, you not only have beaming of the power, you also have a Doppler shift of the frequency of the emitted radiation. So if you happen to be in the direction of motion, then the frequency is blue shifted. If you happen to be against the direction of motion, then the frequency is red shifted, so and so on and so forth. Okay, so now let us talk about the spectrum. As I already mentioned, we receive electric and magnetic field, which are coupled, of course, because H is just n cross E. So, so let's take the electric field. It has a time variation, and we express the time variation of the electric field as a combination of multiple sinusoid of different frequencies, which we call omega here. Okay. So a large number of combinations of sin omega t, cos omega t kind of variations, which together can be written as e to the power of I omega t. So we want to express the time variation of the electric field as a combination of different values of e to the power of I omega t type variations. So let's say I have a charge which is oscillating up and down in exact sinusoidal fashion. Now I know my electric field that I receive is proportional to the acceleration. So if the charge is oscillating up and down in a sinusoidal fashion, the acceleration itself is also sinusoidal. So therefore, the electric field, which is proportional to acceleration, is also sinusoidal. So the electric field that I will receive then, I'll measure at the observer, radiation field, will have a sinusoidal dependence on time of a frequency which is equal to the frequency at which the charge is oscillating. So this spectrum will then be monochromatic, containing a single frequency, because I can describe the received electric field in terms of a single sinusoidal oscillation. But this is, of course, not the case in general. In general, the electric field will have an arbitrary variation in time, and that arbitrary variation I can, in principle, write as a combination of many sinusoidal variations. The technique to do this decomposition is called Fourier transform. So let us take v dot of t as the acceleration of the charge. So the electric field that I receive is proportional to v dot of t. I multiply it by e to the power of I omega t and integrate it from minus infinity to infinity. So this result is then a function of omega. So I use different values of omega to carry out this integral. I get different values on the left-hand side. And this quantity is a Fourier transform of v dot of t. This is a function, however, not of time, but of omega. So we call that v dot of omega. And if we know v dot of omega, v dot of t can be reconstructed by the inverse Fourier transform, v dot of omega e to the power minus I omega t d omega. So v dot of t is then expressed as a linear combination of many different components, each with a different frequency omega, and those amplitudes of those components are given by this v dot of omega. Okay. So now that I have decomposed my time varying electric field in terms of these individual components, I can also write the power, the Larmor formula power that I wrote before, in terms of this v dot of omega. And my I of omega now, the intensity as a function of frequency, can simply now be written as q squared, which we already had, times v dot of omega whole squared, instead of v dot of t squared, which was the total power emitted in the time domain. So this is now the spectral power. So at different frequencies, I will have different values of this I of omega. And so this intensity as a function of omega then gives me the spectrum. So therefore, if we know the acceleration profile of a charge, then we know the time variation of the electric field that we receive. So we just simply take that time varying electric field, do a Fourier transform, get v dot of omega, and then put it in this expression, and I get I of omega, which is my predicted spectrum. So that is how, from the time varying acceleration of the charge, I can compute the expected spectrum that the charge will produce. Now I introduce this quantity I of omega. This is intensity per unit frequency band. That is energy crossing per unit area, per unit time, per unit frequency band. And we can make a further definition of energy crossing per unit area, per unit time, per unit frequency band, per unit solid angle, which now also takes into account the direction that the radiation is coming from. Then that quantity is called the specific intensity. It's called I nu. Intensity, which is energy crossing per unit area, per unit time, per unit frequency band, and per unit solid angle. So this intensity I nu emitted in one frame will not be the same in another frame because of the effects I have already mentioned. A, there will be relativistic beaming, which will cause the intensity to change from one frame to another moving frame. Secondly, the frequency itself will be Doppler shifted. So the definition of the frequency at which you are receiving the radiation will also change. However, it turns out that if you take this ratio, that is I nu divided by cube of the frequency, both these are transformed functions now. They both change from frame to frame, but this ratio remains constant. So this I nu over nu cubed is known to be a Lorentz invariant, and this is useful for trying to compute what kind of intensity we will see in a moving frame, or if the charge is moving with respect to us. Now, so far what we have talked about is spectrum of radiation produced by a single particle. But in all practical situations, we are not seeing emission from one single particle at a time. Any emitting source is composed of a very, very large number of charged particles, and they're all emitting simultaneously. But they all have different velocities, they all have different accelerations, they all have different energies. So they're not all producing the same identical spectrum. And they're all also moving at different speeds with respect to us. They're moving in different directions with respect to us. So what we actually see from the source is a sum of the spectrum received from all these individual particles. So what will be the shape of this spectrum, which we receive from a population of particles? And that we can derive by integrating the energy spectrum of a given particle over the energy distribution of the charged particles. So energy distribution of the charged particles, which means also the velocity distribution. So that actually shapes the spectrum of a given source. Now we can talk about two broad classes of energy distribution. One is something that you would be already familiar with, and that is thermal distribution, where the energy of the charged particle, the number of particles as a function of energy, is distributed according to the Maxwell-Boltzmann distribution, which I have shown on the left-hand side diagram through this red line. Now, there are situations where the energy distribution of charged particles in a source differs from this Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution, as you would already know, is defined by a single parameter, which is the temperature of the system, temperature of the distribution. However, there are situations encountered fairly often in cosmic sources where the energy distribution of the particles involved is not exactly Maxwell-Boltzmann. So there are departures from the Maxwell-Boltzmann distribution. So any distribution that is not exactly a Maxwell-Boltzmann distribution cannot be described by a given temperature. Of course, Maxwell-Boltzmann distribution will be different at different temperatures. So a distribution could be describable by a Maxwell-Boltzmann distribution at some temperature. If it is, then it remains a thermal distribution. But if it cannot be described by a Maxwell-Boltzmann distribution of any temperature, so whichever temperature you take, there will be deviations. So in that case, such a distribution is called a non-thermal distribution. One of the common examples of non-thermal distribution is a power law. Now here, I have shown that in blue. Notice that the horizontal axis here is log of energy, and the vertical axis here is log of number of particles. In such a diagram, a power law is a straight line. So which is shown here in blue. So a power law distribution typically has larger number of particles compared to Maxwell-Boltzmann distribution at either end of this energy distribution. So that is, compared to the peak, there will be excess particles both at lower energies as well as higher energies. A single power law non-thermal distribution has that character. So now if we use this energy distribution to sum up the individual emissions produced by these different particles to express what we will see at the observer, then we will see a radiation spectrum which results from it. And schematically, that is shown on the right-hand side. So for example, a thermal spectrum will have typically a shape like this, where there is a well-defined peak, which is characterized by the temperature of the particle energy distribution. So radiation spectrum will carry the signature of that temperature, just like the Blackbody function that I was talking about before. On the other hand, a polar distribution, which does not have a characteristic energy in the energy distribution of the particles, will translate to a polar distribution in radiation, but it does not have a characteristic frequency of emission. So a thermal spectrum will have a characteristic frequency of emission defined by temperature. A non-thermal emission does not need to have so. A polar distribution in particular will not have any characteristic energy energy defined, a pure polar distribution. So here again, you see that compared to a thermal radiation, let's say this thermal radiation represents the spectrum of a star. So now if you have another source where the particle energy distribution is non-thermal, then you see that such sources with non-thermal distribution, polar distribution, will become more prominent at very high energies, so let's say X-rays or even gamma rays, as well as low frequencies like radio. So in fact, at two ends of the electromagnetic spectrum, the very low frequency end, the radio, and the very high frequency end, gamma rays, it is indeed the non-thermal emission from different sources that dominate the sky. And the thermal radiation is typically confined to wavelength bands which go, let's say, from infrared through ultraviolet to up to X-rays. So this is an interesting fact to keep in mind, that the bright sources, both at radio as well as gamma rays, happen to have non-thermal spectrum. Okay, so what we have introduced so far are these specific intensity, which is intensity per, which is energy crossing per unit area, per unit time, per unit frequency range, per unit solid angle. Now, when you have a part of a source where there are some bunch of particles which produce an intensity I nu, this intensity then propagates through the rest of the source, as well as through other material which is there between the source and us. And this process of propagation changes the character of the radiation. So radiation is modified during propagation through matter. And to describe this, we use a formalism called the radiative transfer. In this formalism, we introduce a couple of other quantities. One is J nu, or emission coefficient. This is the amount of radiation produced per unit volume of material, per unit solid angle, per unit time. So that is J nu. It's called emission coefficient. This characterizes the emitting material. So, whatever be the emitting material, it will have its unique character of how much radiation it produces per unit volume, uh, per unit time, and per unit solid angle, and per unit frequency range. We have another quantity called alpha nu, and this relates to the fact that if on any material some external radiation is incident, then the material ends up absorbing some of that radiation. So the amount of absorption per unit volume proportional to the uh, intensity is called the absorption coefficient, or alpha nu. Okay. Now, an interesting quantity is the ratio of these two, emission coefficient to absorption coefficient, which we call the source function, S nu. This S nu is identically equal to the Blackbody function or Planck function B nu for a thermal source. If the particle energy distribution happens to be non-thermal, then the S nu will depart from the Planck function. So the character of the source, whether it is thermal or non-thermal, is fully described by this function S nu. Now there's another quantity we introduce, and that is this absorption coefficient times the depth of propagation or length of propagation through the source, through material. So that is alpha nu ds. D tau nu is alpha nu ds. And this tau nu is called the optical depth. So for a given absorption coefficient, the deeper you go in a source, more light is absorbed, and so you get a larger optical depth. So once we introduce this, then this equation can be rewritten as the equation below, which is d I nu d tau nu is minus I nu plus S nu. And when you solve this, you have a fairly straightforward expression, and you find that intensity, as the intensity radiation propagates through material, is given by I nu 0, which was the incident intensity, which was incident on that material, times exponential minus tau nu, that is the incident intensity is attenuated exponentially because of absorption in the material, plus the material adds the radiation it itself generates, that is S nu times 1 minus e to the power of minus tau nu, right? So this factor is a complement of the factor here, which is the total absorption factor. So some radiation is absorbed and some radiation is added. So as tau nu tends to infinity, whatever was the incident radiation on the material gets completely absorbed. It does not propagate through at all, because it is now infinite optical depth, or which we call optically thick. But if it is infinite optical depth, this term goes to 0, and what you add is S nu, the full value of the source function. And the intensity that emerges, which external observer will see from this source, becomes equal to S nu. So when tau nu goes to infinity, I nu becomes S nu, and if the source happens to be thermal, then S nu is B nu, so it is a Planck function or a Blackbody function. So therefore, at large optical depth, a thermal source will emit Blackbody intensity, and this emission will be received from a photosphere where the optical depth falls below 1. Now, all of these quantities have a subscript nu, which means they are frequency dependent. So it could be that the tau nu distribution for a source is such that it could be optically thick at some frequency nu and optically thin at some other frequency. So tau nu could be large at some frequencies and small at some other frequencies. For example, if there is a resonance, for example, a spectral line, so you could have a large optical depth at the spectral line, but a small optical depth away from the spectral line in the continuum. So with this relatively simple looking description, one can characterize the entire gamut of propagation effects that the radiation has through material. And this is one of the key cornerstones of understanding radiation processes through cosmic sources. So I will stop here today and we will continue from here tomorrow. You can have questions.
So one question is from YouTube.
Yes.
Yeah, Naman Joshi is asking, how do we find out whether the dark lines in spectrum are due to hydrogen in atmosphere of the source or from the dust cloud lying between source and earth?
Yeah. Just from one spectrum, you will not know this, but you will have to look at not only the frequency of the line, but you should also look at other companion lines from the same species, which tells us what is the temperature and what is the excitation ratio of different energy levels in the atoms that are producing these lines. So once we know what the excitation ratio is, then we can tell the temperature of the material which is absorbing. And so what we know is the atmosphere of the star is at a very different temperature than interstellar dust clouds or interstellar clouds for that matter. So from that temperature, we would be able to tell whether the absorption is occurring in the atmosphere or any other colder material in the line of sight. So a single line is not enough to state this, but if you have even a couple of lines, one can easily do so.
Thanks.
I think you can unmute yourselves and ask. There's some question which came up in the chat. But feel free to. So Raisa Camelo has asked, so every cosmic body would be optically thick and thin in different frequencies. Dipankar, you want to elaborate on that a bit? Or you already said so. Yeah.
Yeah. So in general, that is true. As I just mentioned in my previous slide, that is frequency dependent. There are, for example, stars, which at the photosphere is optically thick at almost all the frequencies that we look at. So if it's a very dense material, it is optically thick at almost all frequencies at the photosphere. But there is material which is in the atmosphere and so on, which is optically thin. So it's a combination of some optically thick portion and optically thin portion. But in general, yes, you will have objects which are optically thick at some frequency and optically thin at others.
I have another question. We can use these radiative waves to track down life on other planets. I mean, I was reading through an article and I was telling about the recent work in tracking down if there is life in Venus, and they used some radio waves to detect that. I want to know more about that. I mean, they use the radiative signals transmitted by certain chemical particles in the planet, but you know, I'd like to know more about that.
Yeah, I'm afraid that's not the kind of thing I'm going to cover in this lecture, because I'm going to cover basically the basic principles of radiation. But as you can see, uh, the the character of a source depends on the composition of the material it is composed of, right? It depends on the kind of material it is composed of. So if there are certain molecules, for example, this phosphine molecule or something like that, which was seen in the uh, Venus atmosphere, every molecule, every species, every atom, every molecule have their characteristic transitions. And if you can identify such a transition, then you can figure out what molecules are present, or what species are present, what atoms are present, what ionized species are present, what molecules are present. And in case of the Venus experiment, that is what was done. One specific spectral line was identified to be from a particular molecule. And then you ask the question as to how come this molecule is present there. And in trying to answer that question, one of the answers was that it could be biologically produced. So that is the inference. The observation is a spectral line, and the spectral line is produced by a certain species. So identification of that is the second step. And the third step is trying to interpret is how did material, this particular species come to be there. And it is in that step you invoke the origin of these molecules, and uh, say possible origin could be biological activity.
Right.
Thank you. Did they use a radio telescope to track that down?
Yes, millimeter wave telescope. It's ALMA.
Oh, thank you. Thank you so much,
Yeah.
sir.
Yeah.
Raisa, just to add to it, I think that experiment was redone, our data relooked at, and the detection was not confirmed. So
Yeah.
it's still debatable whether it is, real detection or not.
That is correct. But in general, that is
Thank
how
you.
one would go about it. I mean, one would go about
That's
trying to look for molecular lines. And
That's
then,
right. Yeah.
yeah.
There is Himadri Saha who is asking the sources showing power law spectrum to the particles show some kind of distribution. You've actually shown the slide, but maybe for his benefit, you can repeat it.
This is the distribution, right? I mean, you're talking about distribution in energy or space?
The motion distribution in space.
Motion distribution is the distribution of kinetic energies, right? And what I've shown here is the distribution of kinetic energies. So you have a smaller number of particles at larger kinetic energy, larger number of particles at smaller kinetic energy. And this is described in a fashion where the number of particles as a function of energy can be written as n proportional to e to the power of some minus alpha, right? So e to the power of some minus p. So that p is the power law index, and so then in this log-log diagram it will have a straight line. So so yes, shows is that distribution that you are referring to. But in space, it could be anything. It could be isotropic distribution of particles, or it could be even beamed distribution of particles. It could be uh, confined. It could have large bulk motion. So all of that is possible. So there are diverse characteristics of the spatial distribution of these particles, but energy distribution is given by this power law.
Okay.
Sir,
Sorry, go ahead. There's one question in the chat which says from Somya, which says, can you elaborate a bit on limb darkening, which is dependent on the optical depth, I guess? You want to say a little bit on that, Dipankar?
Yeah, okay, I can talk about that. So I don't have a diagram to explain it, but so let's go back to this spectrum. So you see that the sun emits a spectrum like this. Let's take this yellow line. So if you look at the photosphere, the photosphere, if you look at the photosphere directly, normal, perpendicular to the photosphere, you take a radial line joining the center of the sun to you, and you look along that line. Then your line of sight, you're going from outside, and you keep going in, and you will encounter more and more material. It starts with the atmosphere, which is the outermost parts of the sun. And as you keep going in, you will accumulate more and more material, and you will at some point hit a situation where optical depth has become 1 or less than 1. So that is the point which is the photosphere, and you will start seeing a black body from that point. And the temperature of the black body will be the value of the temperature of the gas at the photosphere at that point. Now, it so happens that in any star, including the sun, temperature is not constant all through. The temperature is highest at the center where nuclear burning is going on, and temperature keeps dropping as you come outside. Your line of sight is going from outside to in. So this radial line which I talked about, it will go to a certain point and find optical depth equal to unity, and you will see a temperature which is at that point. Now consider a line of sight which is grazing the sun at the edge. So now, because you are looking at it edge on, for any small distance you go through, the actual amount of material that you pick up is larger than if you are going radially straight through to the center. So the optical depth for a given set of radial layers, if you look at it edgewise, is going to be larger because you have gone to larger distances, you have picked up more material. So the point at which you will hit optical depth equal to 1 is now located at a larger radial distance from the center of the sun than if a line of sight was going directly to the center. And since the temperature decreases outside, the value of temperature at that slightly outer radial point will be smaller than the direct line of sight. And so if the temperature is smaller, the emission is lower, and your black body moves to a lower energy. And so therefore you will see, compared to the direct line of sight, a little darker emission. And this is the limb darkening. So you go to the edge of the sun, your tau equal to 1 surface comes at a larger heliocentric radius than straight through a central line of sight. And the lower temperature there gives you a darker image. Is that
Okay,
clear?
sir. Yes, sir. I just missed one part as you were saying that there will be variation of the two things as you encounter more material, the direct line of sight and the actual line of sight which you were talking about. Like, why is
Yeah.
that happening? Like a bit, if you can.
Geometry.
Okay,
If
sir.
you look at something tangentially,
Yeah, got it.
Then
Yeah, got it.
yeah, you see more material for a given distance
Yes, sir. Fine. Okay.
as opposed to seeing it normal. Yeah, it's just geometry.
Thank you, sir. Fine.
So maybe we'll close now because you need a little
Sure.
bit of break before you start off at 11:30 again.
Yeah.
Dipankar, what we'll do is we'll just take a gallery shot for the record. And
Okay.
yeah, maybe let me, if you exit your slideshow, I'll just put it in full screen and. Okay, let me see side by side gallery. So can I request you all to just put on the video on briefly?
Yeah, my video is on right now.
Yeah, video is on, yeah.
Yeah.
Rest of you participants, can I request you to just put your video on briefly so that we'll just take whoever comes in. Prakash, Upamanyu, Roshan, Somyadeep, Jamir. So can you all just put your videos on briefly? We'll just take one